All right, hello. We are covering 7.5 vectors and algebraic approach. We did not do the geometric approach, which was in an earlier chapter. Um, so you just need this section here. Okay, so take notes, 7.5 vectors. So I'll do a real quick review of vectors in case you have never seen them before. Okay, so vectors, an algebraic approach. Okay, so what we're going to look at here when we talk about vectors, we're going to look at what it looks like when a vector is in standard position. Um, we are going to look at what a unit vector is. If you know what a unit circle, you can imagine what a unit vector might be. We're going to take a look at what the magnitude of a vector is and how to find it. And then we're going to look at how to do some calculations with vectors. So we're going to look at how to add them, subtract, and do scalar multiplication. So a scalar is just a real number. And we are very specific about this here, that we are doing scalar multiplication, because here in what is this called? Vectors. We can actually do two kinds of multiplication. We can do scalar multiplication, where we take a vector and multiply by a real number. Or we can take a vector and multiply it by another vector. So you can kind of uh, think of polynomials. So like with a polynomial, you can take a polynomial and multiply it by like 3, right? And you would distribute the 3. And then you could also take a polynomial and multiply it by another polynomial, right? Okay. Okay. So here we're going to be looking at these things. Okay. Oh, and then we're also going to look at component form, and vector component form. Okay, so let's first start with what a vector is. Okay, so if you are taking physics or any engineering courses, then you might already know quite a bit about vectors. So vector. It is a quantity that has magnitude, and direction. And we use vectors to represent forces. So that's why you'll see it in physics or in engineering courses. So a quantity that has magnitude and direction. So maybe you have a rope that's pulling on an object in this direction. So that's why the direction is important. And your object is being tethered at the end there, pulled in that direction, and this here would be its magnitude. It has a magnitude of 12. So here, when we're just talking about vectors by themselves and not necessarily representing any forces, then the magnitude actually just it just represents the length. Okay. All right. So notation. All right. So we can if we have a vector v, we could write it like this. That's just an arrow on top, vector v. If it's a vector that starts at one point A and goes to another point B, then we can also call it vector AB. Another way we could write it is like this, X, Y. Okay, so this is a component form. Let's put that over here underneath. So this one is in component form. I'll talk a little bit more about this in a bit. And then it can also be written like this, x times vector I plus y times vector j. Okay, and so only the I and the j are vectors. The x and y are just real numbers. And this one here is, this is a component, vector component form. Vector component form. It's also depending on which book you use. So your book calls it vector component form. Some books will also call it IJ form. IJ form. Okay, so it just depends. Okay, the magnitude. So let's take a look at that. Magnitude, how do we find it? All right, so here, so the magnitude, like I said, if we're not really talking about forces for just the vector all by itself. So normally, like the magnitude would represent the amount of force. But if we're just talking about just a vector in space, then the magnitude is the length of the vector. Okay, and we know how to find the length of a line, right? Like if you had 2 points in space, we know how to find the distance between 2 points in space. We just use the distance formula, right? Okay, so, and we know that the distance formula came from the Pythagorean theorem, right? Because if this is in an xy plane, right? And we have these 2 points, and then we just do the Pythagorean theorem to find that distance. Okay, so same thing here. So this is the notation for magnitude. Okay, magnitude of vector v, and that is equal to the distance formula or Pythagorean theorem, where it's x2 minus x1 squared plus y2 minus y1 quantity squared. Okay. We have two special vectors, the zero vector and the unit vector. Let's just point out some characteristics here about them. The zero vector. So the zero vector has no direction and no magnitude. No direction, no magnitude. That's like if you're flying, you have zero wind, right? Okay, so and we use the zero to denote the zero vector. And then the magnitude of this would be 0. Okay, and then we have the unit vector, just like the unit circle. Oops, I was about to write circle. Okay, unit vector. The unit vector, just like the unit circle, has a length of 1. Has length equal to 1. Okay, just like a unit circle has a radius of 1, a unit vector has a length of 1. And we'll talk more about unit vectors in the second part, I believe, okay, of this video, of this 2-part video, okay? All right, let's talk about standard position. Okay, so here in this drawing here, this vector is just kind of floating in two-dimensional space, right? Just some random spot. Now, when we talk about a vector being in standard position, then it's not just hanging about in two-dimensional space randomly. So standard position, it's a vector with an initial point, at 0, 0. Okay, so that's for all standard position vectors. They all begin at 0, 0. Unlike this one up here, this is just kind of maybe 0, 0 is over here, right? Your x and y axis are over here and 0, 0 is here, right? Or maybe it's over here, right? So this is just kind of floating in two-dimensional space, and this is its initial point. That's the terminal point. Okay, so here, if it's in standard position, it's just starting over at 0, 0. Okay, so if I have this vector v hanging about in two-dimensional space, right? It's not in standard position, but then if I move it so that the tail is at the origin, then I would have this one here, and you would see here that they still maintain the same direction, right? And the same magnitude, okay? And so now there is just this terminal point. And so here we can call this vector x, y. Okay, so that's the component form. And if I want to find the magnitude of v, then I don't have to do this really long formula because now x1, x1, y1 is 0, 0, so I don't need them. And I can just say x squared, x squared plus y squared. Okay. So let's go ahead and do that. X squared plus y squared. Okay, so if you see a vector written like this, that means it's in standard position, which means that it starts at 0, 0 and goes out to this point xy. Okay. And make sure you see the difference in the notation here because remember, a point xy uses parentheses. Vector xy uses these funny symbols here. Okay. All right. Let's take a look at this example. Let's draw the vector 5, -2 in standard position. In standard position and find its magnitude. Okay, so in order to draw this, remember this vector starts at 0, 0 and goes all the way out to 5, -2. So let's go ahead and draw that. Okay, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, so 5, -2. So I'm going to travel to the right. 1, 2, 3, 4, 5, and then down 2. So right here is where my vector ends. Okay. All right, so vector v, we'll call it vector v, is 5, -2. And then the magnitude of this vector will be the square root of 5 squared plus negative 2 squared. So that is going to be 25 plus 4, which is the square root of 29. Okay. Okay. Let's see. All right, so let's take a look at adding and subtracting vectors. All right, so suppose that we are given these vectors. Suppose we're given vector u, and vector u is in standard position and goes to the point 6, 2. Vector v, also in standard position and goes to the point negative 3, 5. And suppose you have to find the following. Suppose that you have to find u minus v. Okay, so when we do a vector subtraction, then all you have to do here is you take your two vectors, 6, 2, and negative 3, 5. And what you do here is you just subtract your x components, and then you subtract your y components, and then you'll end up with a new vector. Okay, so here you would do your 6 minus negative 3. And then over here you would subtract your y components, so 2 minus 5. Okay, so here you would get 9, and here you would get negative 3, a whole new vector. Okay, so let's kind of take a look at and see. Actually, we'll do that in a minute. Let's finish letter B. And then suppose you have to do u plus v. Okay, so then here, so similar to subtraction, except now you are going to add the x components, and then you will add the y components. So here you would do 6 plus negative 3, and then over here you would do 2 plus 5. And then here you would get a whole new vector. You would get the vector 3, 7. Okay. All right, so let's take a look at what this means visually. Okay, so let's do this. All right, so here's what this means visually. So let's go ahead and draw these two vectors, and I'll do one for each operation, one for the subtraction, one for the addition. Okay, so this is for A. All right, so we have vector u, which is at 6, 2. 1, 2, 3, 4, 5, 6. 1, 2. Okay, so this is vector u. Ah, that's not very good. Okay. All right, there's vector u. And let's draw vector v. Vector v is negative 3, 5. 1, 2, 3. 1, 2, 3, 4, 5. Okay, and so here we have vector v. Okay, and then for the subtraction, we end up getting 9, negative 3. Okay, so this is, how far is it? 6, 7, 8, 9. 1, 2, 3. Okay, I'm going to go ahead and do this in a different color. All right, so here I have vector 9, negative 3. Okay. All right, so what we have here, 9, negative 3, is actually, if I take, let's go up here. So if I take the negative of this vector, then I would get 3, negative 5, right? So let me do that in green. 3, negative 5, 3, 4, 5. So 3, negative 5, which is here. Okay. So this one is a negative v, okay? And so what happens is this 9, negative 3 is the diagonal of this here parallelogram, okay? And when we do it for B, we get the same sort of thing. So let me go ahead and draw the two vectors again here. And we have 6, 2, 1, 2, 3, 4, 5, 6, 1, 2. So that's vector u. And negative 3, 5, 1, 2, 3, 1, 2, 3, 4, 5. Okay, so this one is vector u, and this one is vector v. And then we end up with 3, 7. And again, I'll do that one in purple or pink, whatever this color is. 3, 7, 3, 1, 2, 3, 4, 5, 6, 7. And we see here that this is also the diagonal of this parallelogram. Okay, um, this diagonal of this parallelogram formed by two vectors is a very special vector. This diagonal is what we call the resultant vector. Okay, all right, but I just wanted you to see that because it's kind of cool. Okay, all right, let's take a look at scalar multiplication. Again, you probably deal with resultant vectors if you're taking a physics class or an engineering class. Okay. All right, so let's take a look at scalar multiplication. And again, vectors are used for forces to represent forces. Forces that act on each other, forces that act on an object. Okay, so suppose that I have this vector, 2, 3. And I need to find this scalar multiplication, which means multiplying by a real number. So 3 times vector v. Okay. So 3 times vector v is what you might imagine it to be, 3 times this vector. And you would multiply both components, x and y, by 3. So you would get 3 times 2, which is 6, and 3 times 3, which is 9. Okay. And let's take a look and see what that looks like visually. Okay, so let's take a look at vector v, which is 1, 2. Okay. Vector v is 2, 3, so right over here. And then 3 times vector v is at 6, 9. And let me just go ahead and do this. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So all the way up here. Okay. And what we end up seeing here, this is your 3 times v vector, is exactly that. We see this longer vector, which is actually 3 of these vector v's. Okay. All right. Okay, why don't you try these? Okay, so go ahead and try this here. All right, if vector u equals 2, negative 4, and vector v equals negative 7, 5, see if you can find the following. Okay, I'll give you 2. See if you can find u plus v, and then see if you can find 3 times u minus 4 times v. Okay, so go ahead and hit the pause button and then come right back. Okay. All right, so vector u is 2, negative 4. And I'm going to add that with vector v, which is negative 7, 5. And so I'm going to add the x components, so 2 plus negative 7 here, and then negative 4 plus 5 over there. Okay, so 2 plus negative 7 is negative 5, and negative 4 plus 5 is 1. Okay, so you should have gotten the vector negative 5, 1 when you added those 2 vectors. All right, this one is going to be 3 times vector u, which is 2, negative 4, minus 4 times vector v, which is negative 7, 5. So here I'm going to distribute the 3 to the 2 and negative 4. I'm going to get 6, negative 12. Over here, it's up to you to decide if you want to keep it subtraction and only distribute the 4, or if you want to distribute the negative 4 and turn this into addition. I'm going to go ahead and distribute the negative 4 and then add my results. Okay, so I get 28 and negative 20. Okay, and when I add the x components, I get 34, and when I add the y components, I get negative 32. Okay. Okay, so that is it. Hopefully you got the same answers that I did. If you have any questions about this quick intro to vectors, just make sure you email me or text message me. And don't forget to check in for attendance.